G'day chemistry students, we have another video covering dot point 2.2.3. In this one we're going to be looking at how to determine empirical formula. Let's get straight into it. So first off, we've already looked at empirical and molecular formulas, maybe even if we haven't talked about them explicitly in previous lessons. So already if we have molecules, especially covalent ones, we've written out these covalent or molecular formulas before. Things like carbon dioxide has a molecule of 1 carbon, 2 oxygens, or water dihydrogen oxide has 2 hydrogens and 1 oxygen. But there are more complicated molecular formulas here down the bottom as well, and I'm hoping what you can appreciate is that the empirical formula that we have over here is the simplest whole number ratio of all of the elements. So if I have a molecule of CO2, they are already in the simplest ratio of elements. However, if I have a molecule like this down here, C6H10O3, I can divide all of those element numbers by 3 and have a formula down here which follows the same ratio of carbon, hydrogen, and oxygen, but would not be representative of all of the atoms that are present in a single molecule. And this is known as an empirical formula. Now, for covalent molecules, empirical formulae don't really come up at all, or certainly not that much when we are looking at topics in this chemistry course. However, they are significantly more important when we start looking at ionic compounds. So already we've come up with the idea that cations and anions can exist in certain ratios depending on their balance of charge. So for example, if I have a Ca2+ here, a calcium, and a sulfite ion, SO3 2-, those two charges balance each other out, and in a compound they exist in a 1-to-1 ratio. So we don't put any additional numbers down for the empirical formula that we would usually write. But for something like barium phosphate, the barium has a charge of 2+ and the phosphate has a charge of -3. So to balance out the two charges, we need 3 bariums, or 3 positive 2 charges, for every 2 phosphates, or every 2 -3 charges. So if we were to multiply out the charge, there'd be in total 6 positive charges and 6 negative charges that balance each other out, and we are able to see the ratio in which these particles exist by looking at the smaller numbers at the end of each ion. Now that becomes really important for ionic substances in particular, because we actually use empirical formulas all the time. We don't have molecules of ions that look like this because they follow a repeating pattern or a crystal structure like we looked at a few weeks earlier. Now, when we have that pattern or crystal structure, we are not going to be able to write out a count of every single particle. Imagine one that has, thousands, if not hundreds of thousands, if not millions, or even more particles all formed together to form a single crystal. We're not going to be able to count all those one by one. So what we do instead, and what becomes really useful when we're doing all sorts of various calculations, is to use an empirical formula, the simplest whole number ratio of elements. So for example, for sodium chloride, it's written NaCl. Despite there being more than one sodium and chlorine particle, they exist in a ratio that is exactly 1-to-1. Now, for these calculations, what we're going to be showing are examples of reactions that occur and using the information that's there to determine an empirical formula based on masses or gravimetric analyses that has been done. Let's get into it. So let's have a look at this empirical formula practice question for this video. Note that the reaction that I'm talking about, at least as far as my research can go, is not one that actually works in practice. It's a completely made up and theoretical reaction, but for the sakes of this question, it's quite simplistic and easy to work with, so we're going to roll with that one. Now, what we've been told is that aluminium oxide is formed when 10 grams of aluminium is heated in the presence of oxygen. When the oxide has formed, its new mass is 19 grams. Determine the empirical formula of the newly formed aluminium oxide. So the first thing that we probably need to think about is what's actually happening in the process, what reaction is being described. And what we should be able to see is that aluminium is a reactant of some description. It's a solid, and it's reacting with oxygen gas. So usually we would assume, unless told otherwise, that that's O2. That's a gas. And that it's forming this thing here, aluminium oxide, or ALO. But what we don't know is the ratios of the aluminium to the oxygen. We have not been told that. That's in fact what we're trying to find. We are trying to determine the empirical formula, the ratios in which the aluminium and oxygen will exist as aluminium oxide. So what I'm going to be doing is placing an X and a Y down the bottom for the moment, and they're the values that we're actually going to try and find. What we also want to know, and what we can probably do later, is write up a full balanced equation, and that will be based on the empirical formula of the aluminium oxide. Now, that's not something that's explicitly asked for in this question, but something that we might do as a little bit of an extra exercise towards the end. So, some information that I can see to start us off. What I can see is that we start with 10 grams of aluminium. So, the mass of aluminium at the start and at the end, the mass of aluminium that will be inside the aluminium oxide at all times should be 10 grams. Now, we're assuming that the aluminium mass will be the same here and here at all times. That assumption's being made and assuming that all of the aluminium has completely reacted. What we've also been told is the new mass, and the new mass is 19 grams. So that's the mass of our aluminium oxide, whatever ratios they exist in, that is 19 grams. Now, to go any further with this question, something else that we'll want to know is, well, how much oxygen, or what is the mass of oxygen that reacted? So how much oxygen, or what was the mass of all of the oxygen atoms that reacted for this reaction? And it's actually pretty easy to determine that. And it's based on the other masses that we have. Aluminium oxide is only made from all of the available aluminium, which means any remaining mass would have been our oxygen. So the mass is something that we can calculate really quickly, the mass of oxygen. It's simply going to be 19 minus 10, which is 9 grams. Now, at this point, we know the masses of both the aluminium and the oxygen that were reacting. And to determine the empirical formula, what we'll actually have to try and figure out is the ratio of particles that reacted. And if we're talking about number of particles that reacted, again, we're referring back to this concept of the mole. The mole is just a count of particles in a digestible form. So what I'm actually going to want first, before I do anything else, is to take these masses and find the number of moles of aluminium that reacted, as well as the number of moles of oxygen that reacted. So the number of moles of aluminium reacted is going to be the mass of the substance reacted divided by its molar mass. So we already know that the mass is 10 grams and that the molar mass, if we were to look at the periodic table, is 26, where are we? 26.98 grams per mole. And for the number of moles of oxygen, we know that it's also going to be mass divided by the oxygen's molar mass. The mass of oxygen that reacted we already determined to be 9, and the molar mass is always 16.00 grams per mole. From here, we can determine the number of moles by doing some simple calculations, and we can do that for both at the same time. So for the aluminium, let's get rid of that. We have 10 divided by 26.98, and that is equal to 0.3706. And I'm only going to do 4 significant figures. That's more than enough. In fact, we're going to be reporting a lot of these values to 2 significant figures because they're the lowest number of significant figures up the top. And that's more than enough. For now, we don't have to write out the entire number, but that's going to be MOL for mole. Over the other side, let's do the number of moles of oxygen. So that's going to be 9 divided by 16. And that is 0.5625. 5625 moles. Now, what we should be able to see first off is that there is not an even number of aluminium and oxygen particles that are reacting together, which means that this formula up here is not Al1O1, for example, because they are not reacting in a 1-to-1 ratio. Now, if it's not reacting in a 1-to-1 ratio, what we need to do is determine what ratio those particles are reacting in. Best way to do that is take our two numbers and divide them by each other. So 0.3706 divided by 0.5625, and we'll see what number we get. So 0.3706 divided by 0.5625. Oh, I put a 1 there by accident. Let's change that to a 0. Now the number that I get is approximately equal to 0.6 repeater. It's a little bit off, and that's because we probably weren't using as many decimal places as we should. There is a way to circumvent this to get an exact ratio like I would want, and I will show you that probably when we're in class. You can actually save numbers with 10 decimal places into your calculator. I will show you that technique when we start doing more of these calculations in class, but it is close to 0.6 repeater, which is also approximately equal to, if we convert it to a fraction, 2 over 3. Now, from this information, what I should be able to glean is that the number of moles, or the number of particles of aluminium that have reacted, to the number of moles of oxygen that have reacted, or the number of particles, is equivalent to the following ratio, that is 2 to 3. Middle step, if that didn't make a whole bunch of sense, is what I've done is I've taken the number of moles of each of the particles that reacted of each type and put them into a ratio, which is what I did when I divided them, really, 0.3706 to 0.5625. And by doing the math that I did over here, I've simplified this ratio to one that exists in the lowest whole number possible. So what I know is the aluminium reacted with the oxygen in a 2 to 3 ratio. So if I rewrite my formula like I had before, so I had my aluminium as a solid, I had my oxygen as a gas, I now know that the aluminium oxide had the formula Al2O3. So what I determine with this is, for every 2 aluminium particles, 3 oxygen particles reacted with each other. Now notice that these ratios didn't tell us the ratios of the reactants. It told us the ratio of the empirical formula, or the product at the end. And that is because sometimes our reagents are not just single atoms, but rather they are polyatomic molecules. So this one here is a diatomic oxygen, and it would not follow the exact same pattern of our empirical formula, because you would have not different number of molecules as we were talking about before, but rather we were talking about different numbers of atoms reacting with each other to form the empirical formula. If that didn't make a little bit of sense, that was quite a wordy way of putting it. Please, by all means, ask me for a more in-depth explanation or a different explanation when we get into class. So if we were to balance this formula, what I can observe is that the oxygen clearly is not balanced at all. What I would want to do is increase the number of aluminium oxides that I produce. If we were to balance a formula, increase it to a factor of 2. What that would mean is that there would be 2 times 3. There would be 6 oxygen particles on the product side. And in turn, what that would mean is I'd chuck a 3 out the front here, and that would be my O2 particles. So 3 times 2 is 6 as well. I also have 4 aluminium particles here, and I just have to put a 4 out the front to balance out the individual atoms on the reactant side. That was a little bit extra than what the question expected. Really, they only wanted the empirical formula, but I guess I wanted to show you this process here, this balancing component, to see or show that the ratio of atoms is not the same as the ratio of reactants. And while they can be the same at some times, it's not always the same for all reactions. But anyway, there you go. That's how we can determine empirical formula based on some information about a certain reaction in a written question. Cheers. Thank you for watching this video. In the next one, there's one more type of main or different style of calculation that involves this concept of limiting reagents, but we'll cover that when we get to the next video. Until then, have a good one.